好，欢迎大家今天来到我们的讲座。那等一下我会介绍一下 Fific 教授，他主要专注。OK，hello everyone. I'm very happy to introduce today's speaker, Professor Fific, and he's an expert in cognitive psychology, especially in understanding how our minds processing information and making decisions.
Michigan. I've been collaborating with Professor Young for many years, and part of my reason to come here is to explore and understand better some of these properties of the cognitive functions, such as visual and memory search. Both cognitive activities but can also have an implication in how we use these cognitive abilities maybe to do some practical tasks, such as doctors try to read radiologist recordings and try to determine whether there is some kind of issues maybe the patients. Because this talk will be strictly in English, I try to speak relatively slow. I may really be, feel by because of the presentation, so maybe I start to speed it up, but feel free to stop me at any point. So there's a little bit of a language issue that I hope, you can help me to overcome. And so we are able to communicate I would like to introduce then the topic and focus of the research is these mental processes that are actually running our behavior in behind. They're helping us to use something that we called short-term memory or memory to help us to categorize things, help us to see the faces, memory processes, categorization, decision-making. Would you like the past? Imagine it's what is kind of a stay behind these processes. Typical way to measure these networks and try to analyze them is to collect some responses. So here are the reaction times. Reaction time needed to be completed the entire walk through the network. So this is distribution reaction times. These are response. rectangle among the other rectangles. So it's really easy job here. The reaction times usually a flat line. Doesn't matter how many items you put inside. Detection of the single item just stands out. It's called pop-out effect. And it seems like it is like parallel processing, right? One of the classical findings in Trisman's work, 1988, and others, many people replicated these results. So we look at this paradigm with a new tool. We also look at another tool, which is another method, which is a short-term memory search. Short-term memory is the processes that are helping our consciousness operate because these same results could be explained with the two different architectures with a reasonable assumption. Is that everybody okay with that? References here after the years that it's like an old slide. There's a more and more work is coming about this system factorial technology. So it is the microscope for that microbe, right? How does that work? So we spend some time understanding how the systems factorial technology, or shortly SFT, works. Now we are running into the domain of a little bit, abstract. high one, so this will be low here. Interaction test goes inside the design, is exactly said. So you can start whenever you want. You can from the top or the bottom, but as long as you take the differences in a specific order, low, low minus low, high, take this difference here, minus this difference here. That is the interaction test. You can actually go the other way around. Low, low, you got the same result always, doesn't matter. It's really beauty of these designs. But the point, this is the third test. Nothing's happening. Factors are independent. If there is non-zero, then something is going on here, right? And that's interesting for the researcher. All right, so the second statistics is derived from the first one. Do you see the difference or similarity? What is the, well, there's a symbol of S here, but the structure of the differences is the same. So we take the differences across these four conditions, but replace, and this a function as a statistic, but not as a point statistic estimator, such as mean interaction contrast here. Well, let's call it right name, mean interaction contrast. This is what we use in ANOVA. But survivor interaction contrast is a function of time. Therefore, the time is still there. What does it mean there? This is kind of the big deal. How to calculate this? Quickly down. And this could be component in machine, but this could be human lives too. So longer you are in the game, less likely that you are operating. And then it's connected to the type of factorial condition here. So this is a survival function. It is related to response times. Now, and here's the big deal. When we try to plot these signatures, MICs are over here. SIC, that is the function survival interaction contrast here. And here we can see how they're related to different types of architectures. These are supposedly in our mind, and we don't know that. Serial self-terminating architecture, they can stop, but completing one item, then another one, shows flat. If processing is parallel, terminating, that you see all of them at the same time, what one hand can grab, the function is positive all the time. Always positive, can never go negative. If two processes are parallel exhaustive, then the function is negative all the time. So you need both hands to grab something. we can see how number of indices increase. This is indices for process 1, which is slow, 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 slow. And you can see the other one is fast, 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 fast here. All right, this is the derivation, mathematical derivation. And technically, you can use this to analyze your data. In your study, if you just collect information about each of these, for example, 60. How does it look in the three-dimensional space? Still tolerable. All right, I have a problem with that word. So let me show you. So this is three-dimensional space, Cartesian space, and then you can scroll it down. The blue dots here are factorial conditions for one type, and the reds are factorial conditions for the other type. The blues are, in this case, target absent answers. The reds ones are target present answer. But it's pretty crowded, right? When you look at that. Right? It's kind of fun, though, in rotating them. So, for example, here is a high, high, high condition on the three dimensions, variable 1, variable 2, variable 3. This is the fastest condition probably here. The slowest is in between, inside, because it's very close to the reds. Once you're close to the enemy, the opposing group, you're slower always. Further you away from the enemy, you are faster. Okay? And how this situation looks for the 4 dimensions. And now open the gate of 4 dimensions. So please come in here. And if you can tolerate, it is not impossible to visualize the 4-dimensional Cartesian space. You can think of another dimension stacking out of the 3 that is also orthogonal to all of them. So what we can do, we can break it up into another 4 three-way dimensions. In this case, you can see now, for example, for this one, here you have now 4 indices, but one has dot. This is the dimension that is missed in this design. Just remember, reminding us, there's one more dimension that is missing here in this description. All right, but we cannot really operate in that space. All right, it's really fun to look at them. Visualization is difficult, and you're stacking up more and more different conditions. The thing is, who cares? As long as I can create the conditions that follow this kind of design, I just have to plug them in this equation and I'm good. What are the predictions then of 2, 3, and 4? And these are the predictions. Now I have, these handouts for you guys. You need to help me. So I don't have that many. So you may need to choose maybe to, I can distribute half of them here. So you maybe share with someone who is sitting near you to look what is going on here. And I need your help later on to try to visualize some of these results. All right, that was okay. Everybody survived, coming back from a 4th dimension, right? Now we're back in the 3-dimensional system. We stay there for a while. And we use these kind of predictions for, this is kind of a master cheat sheet for SIC, survival interaction conscious function predictions, visual predictions for the different architectures. We need it later on. We're going to be looking at the results. All right, so overall, you can see if you go across columns here. So first we have different architectures, serial stuff. Terminating, if you remember, these are 2 serials. These are 2 parallel architectures, the most popular ones. And if you go across columns, we are increasing the number of processes under investigation from 2 to 3 to 4. Okay, this column, first column, we know that. We saw already this one. Now, we don't know what is happening to the columns n = 3, n = 4. And you can see the signatures started to change in some cases, but in some cases they do not change. For example, self-terminating will always stay the same. Doesn't matter how many processes we are picking up. So this one will not be really diagnostic in terms of the number of processes. Serial exhaustive, which is very popular in a visual search, as I said, serial processes that you process all of them, actually shows very peculiar behavior. Each time we add one more process, it flips. Function flips up and then flips down. And while doing the flipping, it is adding one more intersection. 1, 2, and 3 here. This is very diagnostic for the serial systems. None of the other architectures predict that easily, this kind of a shape change. Parallel self-terminating stays the same, always positive. This is interesting. And parallel exhaustive flips. All right. Is everybody okay so far? A little bit of a taxing on your memory, but this is why we need these handouts. I explained what happens if you flip across items. Now, let's go back to your masterful skills of using ANOVA. Okay? It is similar to two-way ANOVA, three-way ANOVA, four-way ANOVA. How many tasks you can do in four-way ANOVA besides main effects, interaction effects? Huh? Oh, I don't want to hear the answer. Just think about that. There are other types of tests that one can use in the four-way or three-way ANOVA, or even two-way ANOVA, which are not including only looking at the main effects and interaction effects. For example, one can look at the simple factorial tests. What is a simple factorial test? Well, if you have four-way ANOVA could be broken down into 4 simple tests. So that means one of the variables will be kept constant, like a dot here, while the others are actually allowed to vary. We just group the data differently. This is simple interaction test. And you can go in further. You can apply the simple interaction test to look only, oh, is there any interaction between factor 2 and 1 while the others are fixed, or doesn't matter what the values are of the 2. So for example, you can have 8 of these tests. So here's the deal. Recursively, if you look only at n equal 4 data, you could also conduct these simple tests, and this signature would still apply as if you were running the n equal 2, n equal 3 tests in the full study. All right, so the same signatures should hold if you're using regular main effect, interaction effects for the full size, or if you're using simple tests, if you're degrading, breaking down 4-way or 3-way ANOVA to smaller components, which is kind of very handy. A little bit too much information I can feel right now, but I'll show you later on how we're going to use that. The point is that all the signatures we hold in both directions. All right, let's see what we have. First, start with a memory study. Now we go to the real details. We run a memory research, short-term memory research. Memory study was looking at, first we're going to look at the n equal 2 case when you only have 2 processes. That means we have 2 memorized items in a set only. And n equal 2 looks like this. Subject has to memorize 3-letter words. That doesn't make sense. Fas, nam, and we varied the similarity, phonemic similarity to the target. So this is n equal 2 case. If the target is phonemically dissimilar to the target, that's called high condition or fast. If it is similar, nam and mal sounds phonemically very similar, and a lot of operation in a short-term memory is be dedicated to the phonemic representations. So this makes high-low situation. You can think of the other situations, right, as well here created for the systems factorial tests. And then for n equal 4, we have actually 4 items. It was very hardened subjects, but they did, their job bravely. We collected a lot of data. So this would be an n equal 4 situation. And we can see how they could be changed, to be either similar or dissimilar to the target as well, creating 16 conditions. Here, we need only 4 more. All right, is everybody okay so far? So we're applying systems factorial stuff using double factorial and using 4 factorial designs. So for the double factorials, we created 4 conditions, as I said. And then this is what we observed. This is a published data for a while, and it was easy case. As we can see that, if you look at the chart, when it says n equal 2, the first column, you should be able to recognize some of the signatures. And which signature is this? The first item. Serial exhaustive, that's right. It's S-shaped function. It's approximately similar areas for the positive and negative. And that was the microscope at its use. We can verify that these particular subjects on individual level analysis checked these 2 words in a memory one after another in a serial fashion, and they checked them both. All right, you see that kind of a... Now, how about this guy here, subject 3? If you look at the first column, which signature corresponds to that? Only first column. The function is negative all the time. Which of the functions for the n equal 2 is negative all the time? Exactly right. Very good. We have finder here. Very nice. Parallel exhaustive. That's right. So, and we know it's exhaustive because this was target absent cases. So subject has to search all of them. So that was fixed. But then we didn't know whether it was done in serial or parallel. This guy was parallel all the time. And you know what? This guy is also pilot, happened to be now pilot of the airline, a civil airline. Must be maybe something, in the way he's using a memory, just to retrieve them. But we can see individually different patterns here, and they're very consistent across conditions. And then we can see that some of them are flipping. This subject actually flipped from this condition to that condition, from serial to parallel. Okay, this is n equal 2. Published paper. We did 2004. It was really big paper. We analyzed this situation only, right? So n equal 2. But how about n equal 4? So we can actually have that. We actually have the data, n equal 4. And now, armed with the knowledge, we can analyze what is happening with n equal 4. I'm going to quickly jump here. So we will look at n equal 4 case. All right. And to limit our predictions, we'll be looking at the n equal 4 situation here. So we'll be looking for this signature, that signature, because the conditions that we analyzed were target absent. So that means they have to search for the entire memory sets before they make a correct decision. And then we also look recursively what happens with signatures if we are using simple interaction tests. If you're reducing the number of factors by keeping them constant in analysis while still having the n equal 4 items. So we should be able, for the 3 simple tests, to see this stuff or that stuff for n equal 2. And if the parallel exhaustive happens here, we should be able to see that. So let's look at that. It's broken down into one participant here. So this participant did a lot of work, go through all 16 conditions. Here's the 4-way interaction. This is, actually, that's a data, predictive data, what we expect to see if the subject was purely serial, right? So we can see that you can find in your charts. When we keep some of the factors constant, we see that the signature should flip, like for n equal 3 category. And further flip is provided when the 2 of the processes are kept constant, simple tests with only 2 factors allowed to vary, like a 3rd and 4th factor. Call these pairwise comparisons. They should all look similar, right? And here's the same prediction for the parallel exhaustive. Should be seen flipping across these conditions, but negative, positive, negative here. All right, so here's subject number 2. Does it look in a four-way as any of the signatures? Bottom line, not really. Right? For n equal 4, we should be seeing something that looks, if this is a serial, something that has 3 intersections, and the signature should be going up and down. We only see 1 intersection, and there's a tail behavior here that we really could not really figure out. So overall, n equal 4 didn't really provide much information. When we broken down into n equal 3, we see something that may look like serial. Now look at the column 3, and we can see that actually there are 2 intersections for most of the graphs. Maybe not this one, but seriality started to show up here and here. And if you really press the simple factorial analysis into isolating only 2 factors at a time, we see that all signatures started to align with a serial exhaustive shape for n equal 2 category, negative then positive with approximately same categories. All right, so we can, now what we can see with the microscope is a little bit interesting case, and it's more complex now because we're dealing with a 4-dimensional space of the situations. Some noise is probably starting to dealing with the data, not enabling us to see the final results. But at n equal 2 level, things are relatively clear. There's a little bit maybe parallelity here, although there's a S-shaped, like snake shape here. When we analyze this model, we try to fit parametric model. It showed also advantage of the serial exhaustive. So overall, we can see with the great details that this subject was mainly serial, with maybe a little bit of a dash of parallelity at certain locations. Unlike that guy, subject number 3, can you recognize this SIC shape for n equal 4 category, the 3rd column to the right? Exactly right. So at n equal 4, it shows this is the airline pilot guy. Now let's see what happens when we move to the location. There's a flipping of the signatures, but there's also intersection here and here and here. But generally, it could be maybe interpreted as a serial, or maybe parallel here and parallel here, maybe serial here. We'll look at the 2-way interactions, and mainly we can observe, except maybe this case, that overall this guy was parallel exhaustive all the way, except maybe few of these combinations. So we see the case of a dominant, almost pure parallel processing for the guy, which is consistent actually with his n equal 2 data. The pilot guy processing parallel again. So some of the other networks could be used to explain small differences. And then we're not going to go into the details what are the predictions of these networks, because they will make slightly different predictions depending on the situation. And this is the case of investigation. So briefly about the short-term memory, we see that there's a few more subjects, but I show you 2 relatively clean cases, one pure serial and one relatively pure parallel, which kind of challenges current findings providing in the classical results. If linear, then serial, right? Obviously, one guy was not really serial, was away from seriality, it's completely parallel. So the microscope let us see these differences better. All right, I think I have a little bit more time, so I just go into the visual search study. I show you only a fraction of the results because I'm still struggling with this results. And when I came here, actually, I'm struggling in a positive way because there's a lot of data. But remember that we'll be actually focusing on B condition here, so conjunctive search. And we designed a study where The target is similar to the distractors, so we should be expecting to see something like this. We should expect to see serial processing, right? And the patterns typically recognized by the people in these areas, like there's a 1 to 0.5 ratio of the slopes of these line functions. But more about that later on. So study looks something like this, so remember this item, and then I will flip quickly and next item, and you have to tell me with yes or no, is the item in the set or no. So just say, yell yes or no. Or what would be the yes in Chinese? Yeah, shi or yeah. Okay, let's go with that. All right, so now you have to memorize this. This is display set. Did you see it? Is this the target or not? Then you say no. All right. You see what we have to do. Don't think about it. Immediately say if you see it or not. All right. Here's another try. All right. Here's a target item. Memorize the shape. I briefly show you the next display. Be ready to say yes or no. Is it? Yes. Here, right. Here it is, right? It's not easy though, right? Okay, here's another try. All right, this is a target item. Memorize it well. Here's a display. No. All right, you're correct. The correct answer is no. How do you feel about the task? Was it easy? Not really. When you increase the number of items, did you feel like you slowed down? Did you have access to some of the strategies? You were kind of maybe checking one item by one, right? It could be serial, right? Highly likely. This is called conjunctive paradigm. So you can check them serial, maybe not, right? Let's look at another. Oh, so this is how it looks like. Probably if this is a serial analysis, you'll be checking one after another one and then press the button and make a response. All right. No, the target wasn't there. That's right. And we expect the mean reaction time to increase, right? And usually increases very sequentially. Okay, so how about this item? Now memorize this item. And particularly, you look at the color as well. Shape and the color. Now let's do the task again. Be ready to say yes and no quickly. This time, quickly. I need your curves. Okay, here's this one. 1, 2, 3. No, good. All right. It has to be both red and this particular shape. How about now? Target, and then 1, 2, 3. Yeah, very good. Okay, another one, target, same target. 1, 2, 3. Oops, sorry. Sorry, yeah, just not that. Okay, now. Okay, I'm sorry. Yes, all right. So this was easier task because the target was always in the same color and didn't change the color with the other. It changed it, it shared the shape, but color is just give this thing easily, right? So this is called pop-up effect. And we believe if you process these items in parallel, maybe at the level of the color, the line should be flat. And it's usually like that, right? People learn that the color gives away all the information. They forget about the shape. They only have access to the one dimension. All right, just, gives you an idea. Here's the test, we conducted in our study. And these are the results of the two subjects. Now, I couldn't find better subject in my life if I was trying, but here's the subject 1 and subject 2 after many sessions, around 30 sessions for 3 set sizes, display size of 2 items, display size of 3 items, display size of 4 items. This is target present. This is target absent curve. This is the classical book case of the so-called serial analysis, self-terminating, proposed by many researchers. And the same, another subject, the same thing, like a book case, right? Now, we'll pay attention only with the SFT because remember, with microscope, you can actually look at the small details. You don't have to look at the overall shapes. We can analyze only n equal 4 and this particular target absent case. We can analyze the other cases, but I think this would be sufficient for a demonstration. So subject one, overall, here's a four-way interaction. Does it seems recognizable in the third column? It has positive, it has a little bit of a negative part. Here, does not fit easily. It looks like one of the parallels maybe, but not something that you expect. If it broke down into the three ways, the signature flips here, and it's negative here, a little bit of positivity here, a little bit of positivity here, a little bit of positivity here, maybe two intersection. Doesn't, which one, like which one can you recognize? For n equal 3, the middle category, does it bear similarity to any of the signatures? Serial exhaustive, maybe. When we get n equal 2, it looks S-shaped snake function. The first column goes one intersection. This guy seems pretty much serial, except maybe these two conditions that gets a little bit carried away by the higher, larger positive parts. But overall, we can kind of detect there's a serial processing overall for that person. Although we're not having issues, we're a little bit having issues at the higher levels, and this is kind of discussable. How do we actually deal with these cases here? Why didn't we get clearer signatures as we did in this deconstructed case? Okay, another subjects, similar shape, n equal 3 similar shape. Actually, similar shape and n equal 2. Mainly serial. This is even more stronger serial than the previous case because all these S signatures are aligned nicely and the areas are approximately similar. So, well, it's a pretty uniform case, at least for the two subjects. This brings us to the final conclusion. All right, so we are been talking about developing tools to better understand cognitive processes. We constantly are in need for a device or methods that will allows us to see the intricate detail of these processes. Eventually, this could be done with analyzing brain circuitry, but we know what kind of challenges are in front of the neurologist and the neural modelers. They do not have sometimes clue of what can create the changes. And as well, we step back at the cognitive level, the behavioral analysis, we need better tools to test some of these networks that can maybe provide a precursor to the further generations of the narrowly suggested studies, to be conducting further. And one of the tools that I try to here demonstrate is the use of the system factorial technology, which relies on these factorial designs and non-parametric methods to identify these structures. So we are looking for the better tools. Magnifying glass is getting us better into that point. And we can see that system factorial interaction analysis provides us with further subtle clues about the cognitive structures with more detail than before. How is that? Remember, we are analyzing individual subjects. We not average them, so we keep, the individual processing structures intact. We can see that in a short-term memory task, some subjects really challenging common belief that, straight lines means serial. It could be parallel too. We can confirm that in the two subjects, there's at least good evidence to support seriality as we observe in the classical cases. So that is not really challenging the current findings at the moment, right? What is interesting for R is the clarity with which you can see certain changes. And they are coming, for the particular memory representations, particular places in the memory or in visual field that could be analyzed separately. And we can see that, some subjects, show different types of strategies. So theoretically, there's advantage of the the work is expanding the work of the currently mainly focused on only two processes that exist in the SFT area to n equal 3 and 4 items. Rare research could be found, and maybe none, with the 3 and 4. So this work presents maybe future important step for the development of even better insight by using these methodologies. And finally, I think, these should be the good precursors, to understand and maybe somehow to help narrow analysis, to maybe lead to better conclusions from their own analysis by providing some sort of converging evidence, right? Converging evidence from using these tools to maybe applying some other kind of a narrowly centered tools. All right, guys, I think this is, it. I hope you enjoy, this walk, back through the four-dimensional world, back to our life. And then I hope, that I help, just to stay okay, even after I pour so many abstract things in front of you. But, pick up some messages and always look, for the better tools that can improve our conclusions. All right, thank you. Do you have any questions or suggestions? Feel free to ask or participate in the discussion. You can always feel free to approach me later on to provide you with more details if necessary, or if you decided later on in your life and somehow you put, you store this presentation somewhere at the back of your mind, and then later on you'll be maybe in that situation, say, oh, there was one professor from Michigan here that came with this kind of interesting thing. Maybe I should contact that person, to see, what maybe this could help, somehow in my research project. Yes.
So in your talk, as you mentioned, the SIC predictions is quite smooth, but in the real life, usually after we collect the data and do analysis, usually the data is so noisy. So how to differentiate it's a noisy data or something happened in the SIC shape?
So we are now focusing on the denoising the results. There's a different ways of trying to deal with that. The brute force to deal with the noising is to add more observations. So when you're smoothing data, across conditions, but that costs a lot. And so I open also this kind of a line of thinking. I'll show you how things could be done in a hard way, but maybe one of you guys can think of in the future, quick way to collect the data and to get better effects. So one thing could be to collect more data. We could also use maybe methods to remove autocorrelations for the observations. So this is something that I did a long time ago, but now it's even simpler with some of the techniques. Remember that participants will go through the stages, trials after trial, and there's a belief, that there's a lot of noise in the responses are coming from the effectiveness of the previous trials. And actually, this could be done with the autocorrelation functions such as ARMA or the SARMA models, that you have developed, recently. So part of the noise can be removed that way, maybe detrending the results, maybe creating the better designs. Usually when the data doesn't show big differences, it could be maybe it is a typical issue with the research designs that maybe you should change the values of your manipulations to make it more extreme so they create bigger effects. This is always a big issue. And so we are on the track to finding the best data collection method that will collect lots of data in a small time and relatively accurate.
Okay, so far your talk is about the behavioral test, right? Yeah, and the curve I see is it possible to apply such survival function into something physical data like EG or neural firing? Because some EG in some brain area they are also like up and down and flipping over the average. Yeah.
This is I see. So the question is, again, I would just repeat, whether we observe here reaction times and choice preferences. So the question is, can we use that maybe to brain responses, right? Neural responses. And I don't know. That has to be investigated. So we know how the human behaviors with their output selections with the response time and choice preferences. If we have a clear understanding how brain structures respond in terms of the maybe frequency of the actual potentials or maybe their magnitudes, probably we have to check whether certain types of architectures in the brain, now real brain, could create similar detectable patterns. Answer is we don't know that yet, but I think it would be applicable under the assumptions that we understand some of the basic brain operations, their response and input and output, of the systems.
So
I think this is an excellent idea. Yes. So maybe you could be the one, as a spearheading, the research in the future. Who knows?
And the reason why I asked this problem is because I believe maybe in our brain there are different parts of our brain deal with different information. Maybe some area is about a serial executive and some is parallel. And one of the parallel executive example is about a frog. Frog, they see something moving. If this is small, they think that could be a fly. So they will use their tongue to eat the fly. But if they see something is moving, but it's very big, then the frog will force. So maybe there's something in our brain, in our neuron that represent something, some information like this. So
very interesting. Yes, I would like to learn more about that. Yes, there are some attempts to bring together some of these sequential sampling models close to the work of the neural structures. And that is one good way to do. I don't think it's complete way because the brain operations or neural response is a little bit different than the humans in their final output, which is usually a summary of the many brain activities. But I don't know. I mean, we're talking about the tool, right? Microscopes are used for detecting bacteria at first, but later on we use them, to even look at the orbitals of the electrons in the atoms, right? We also call these microscopes. So maybe such a tool can be used to disambiguate, certain ideas or certain models. Yes, very good. You can also ask a question in your language, and then maybe we can translate it if you think, that's yes, we can do that. So let's do it. So feel free to ask in Chinese. We can find way to translate.
Thank you. You have shown about subjects you use in the experiment, about 3 subjects. How many subjects we need to this this experiment? And do you take into consideration about the characteristics of subjects, maybe female or males, and then jobs and
Yes, this is another excellent question. So there must be individual differences. So what is the important with this approach? It also highlights the importance of focusing on individual subject data. And there's a lot of publications in the psychology and related disciplines about issues with aggregating the individual subjects data in the mean times or some kind of aggregated scores and use them, for the modeling. These are not the same thing if you analyze individual subjects data. So some of the methods has been developed, to deal either with individual subject data analysis or to individually treat the subjects within the model so individual differences are taken into account. And one link, that can lead, to these types of even more advanced analysis using, for example, one of the tests, but not the SIC, the other one, they mentioned this mean interaction contrast, is called hierarchical Bayesian models that one of our colleagues, who presented the work here last year, could also be used, so you can try to model not only the results, but also the individual differences. Now, how many subjects we have, we usually limited by funds. So we had, because they have to do many sessions. So we had 5 subjects, for example, for one condition. For memory stuff, you have around 4 subjects. And it is also possible to run more subjects with a smaller number of trials and then to see whether the results will lead, to the similar conclusions. So then you have to deal more with statistical analysis and see how far, how far you can go, to extending your research, to dealing with these kind of challenges. So Professor Young is doing a lot of research in system factorial technology with a smaller number of trials in a similar domain and goes into maybe larger individual data sets. So, but that's a good point. Yes. Individual difference is very important. So we don't know what happens if males or females, men and women will see things differently, or whether a certain professor, for example, Young is focused on certain diagnostic groups or clinical groups of patients, and do they show differences in their data patterns? So this is one way to go, right? So about these things, so because we are looking at individual differences, such tools are perfectly suited to make quantitative estimates of the differences, between some groups of subjects.
好，没有问题的话，那我们就是邀请杨老师。This is the souvenir from our department. Yes.
Thank you. Thank you.
Let's take a picture. OK，3、2、1。